In this video, we're gonna solve this differential equation here given this initial conditions. Our differential equation is y double prime, or simply the derivative or the second derivative of y plus 16y is equal to cosine 4t. Given the initial condition y0 is equal to 4 and y prime 0 is equal to 7. Using Laplace transform, we can solve this one like this, like applying the Laplace transform to both sides of the equation. First, we'll apply the Laplace transform of the left side equation, Laplace of y double prime plus 16y is equal to the Laplace transform of the right side of the equation, cosine 4t. Now, the formula for the Laplace of this one, the y double prime, is s squared y of s minus s y0 minus y prime 0 plus the Laplace transform of this term here, 16y, is just 16y of s is equal to the Laplace transform of cosine 40 is s over s squared plus 16. That's from the formula. Now, combining these terms with the terms with y of s squared plus this one, 16 y of s minus, since our y0 is 4, negative s times 4 is negative 4s, and our y prime 0 is 7. That's why this becomes negative 7. Negative comes from here, and y prime 0 comes from here, is equal to s over s squared plus 16. Now, manipulating the equation, we can arrive y of s is equal to 1 over s squared plus 16 times s over s squared plus 16. This is from here, and plus 4s plus 7. This one is from here. It's moved to the right side of the equation. That's why this negative 4s minus 7 becomes positive 4s plus 7. And this one here comes from here. After moving the negative 4s minus 7 to the right side of the equation, we then divided both sides of the equation by s squared plus 16. That's why we have s squared plus 16 here. And distributing, we have y of s, we have 1 times s over s squared plus 16 times s squared plus 16. We have the square of s squared plus 16 plus, distribute again, we have 4s plus 7 over s squared plus 16. Now, we have this y of s. Now, we'll use this to find our solution y of t, since our y of t is just the inverse Laplace of y of s. Then we'll take the inverse Laplace of this equation here. Taking the inverse Laplace of y of s is just the same as taking the Laplace of this expression. But since it's easier, since this term right here is, it's easier to find the inverse Laplace, we're gonna leave that later and we'll solve this first. You might be tempted to get the partial fraction of this one to get the inverse Laplace, but you can't express this into partial fraction separating this denominator. Now, since we can't express this into partial fraction, let's assume that the Laplace of t times f of t is equal to this expression here, s over s squared plus 16 raised to square. And the purpose of this letting this expression to t times any function f of t is to find f of t. And if we find f of t, we'll just have to multiply that by t or to t so that we'll find the inverse of this one. Because if the Laplace of t f of t is this expression, then the inverse of this expression is just t f of t, which is one part of the solution of our differential equation. Now, since this here, Laplace of t times any function f of t is just equal to negative d over ds times f of s, since this is f of s, take note that the Laplace, the Laplace f of s is equal to the Laplace of f of t. That's why we have Laplace f of t here, because this here, Laplace of t times f of t is equal to negative d over ds f of s. Now, equating this to s over s squared plus 16 squared, and then taking the integral to eliminate this here, the derivative, and we'll have Laplace of f of t here is equal to the negative integral of s over s squared plus 16 squared ds. We'll multiply 2 over 2 so that this here in the numerator will have 2s ds. We multiplied 2 over 2 because this doesn't change actually the integral. Multiplying by 2 over 2 is just multiplying by 1. So that's why if we multiply 2 here, then we'll have 2 in the denominator. That's why we have 2 here and we have 2 here. The purpose of putting 2 here is because the derivative of s squared plus 16 is, with respect to s, is just 2s ds. Okay, and changing the form here, bringing this up to our numerator s squared plus 16 to the negative 2. The sign changes because we move this expression here in the numerator. That's why this becomes negative 2. And the 2s ds here is this one, 2s ds. Again, it's easier to integrate if we already have the derivative here inside of our inside expression here. So let's copy the Laplace transform of f of t is negative 1/2, this one, negative 1/2, times 1 over negative 2 plus 1 is negative 1. That's why we have negative 1 here. And s squared plus 16 to the negative 1. We have 1 over 2 times s squared plus 16. This one. Because we have negative exponent here, we'll just bring this down to our denominator. This becomes s squared plus 16. And this becomes positive because negative 1/2 times negative 1 is 1/2. Now we already have our Laplace of our f of t. We can find our f of t by finding the inverse of this one. Finding the inverse of this one is easier now because we have a pattern. The inverse Laplace of this one is 1/8 sine 4t. And we have now our f of t, 1/8 sine 4t. Since the Laplace of t f of t is s over s squared plus 16 squared, then from our y of s, we have s over s squared plus 16 squared plus 4s plus 7 over s squared plus 16. Then, to find our solution y of t, we just take the inverse of y of s. Taking the inverse of y of s is commutative, so we can take the inverse Laplace of each individual expression. Now the inverse Laplace of this s over s squared plus 16 squared is just this one, the t f of t, where our f of t is 1/8 sine 4t. That's why we have t from here, and our f of t is sine 4t over 8, or 1/8 of sine 4t. In this one, it's easier to find the inverse Laplace because we already have a pattern. The inverse Laplace of 4s over s squared plus 16 is just 4 cosine 4t, and the inverse Laplace of 7 over s squared plus 16 is just this one, 7 over 4 sine 4t, and that's just it.